Hey guys, just making the key here for the exponential tables and rules practice. So remember that we are practicing exponential functions. Sometimes we have a table of values. It would be nice if we could convert that to an equation. So we could use that equation to get more values in the table if we needed them, or within values, between values, going backwards in time, and we'll do that in number 3. Sometimes we have the equation. It would be nice to have a table of values and perhaps a graph to get more information. And sometimes we have the graph and we can get the table and the equation. So having fluency between all 3 of those is what we're working on here, with all functions, but exponential functions in this case. So 1a and b, we have a table. One has the output values for 0, 1, and 2. 1a and 1b has a gap there in the 1, so that'll be a little bit trickier. But let's start with 1a. It tells us that they're exponential functions, so we can see that here. That's an important piece of information. So we know that it's going to take the form something times something to the power of x. So we need a base b that we raise to the power of the input variable x. And then sometimes we have a multiplier out front. So remember in class we said that if we know the output value when the input is 0, then we know our a value. So with that 0, 1.8, we immediately know a is 1.8. We just don't know what b is. X is just going to stay x because that's the input variable. So the mission is to find out what b is. Now remember, b is a multiplier, a repeated multiplier in the case of an exponential function, and we're going to multiply it by 1.8 to start. So if we make x go from 0 to 1, we're adding 1 more, increasing x by 1, so 1.8 has to get multiplied by that thing to make it turn into 5.6. And to find out what you multiply by 1.8 to get 5.6, you simply divide 5.76 by 1.8, and that happens to be what? I forgot. 3.2. So this equals 3.2. That means our repeated multiplier is 3.2. And so our equation is going to be y equals 1.8. That's not a great 8. That's a little better. Times 3.2 to the x. And then of course you test that. Say if you put in 0 for x, that's 3.2 to the 0, which is 1. 1 times 1.8 is 1.8. It works in the table. Put in a 1, 3.2 to the first is 3.2 times 1.8. Well, there's our multiplier of 1.8 times 3.2, giving us 5.76. So that equation is going to do the trick. And then I put that into a graphing calculator, so if we could either just plug in 3 and then 4, but I put this equation itself into the y equals menu, so it's a little quicker. And it looks like about 58.98. Another bad 8, and 188.74. Okay, moving on to B. Like I said, we have a gap here, but we know there's a multiplier, so we know it's 5 times something has to get us here, and then times the same thing has to get us to 245. So basically have a multiplication of some number twice in a row to go from 5 to 245. Let's see if we can just put what I said into a mathematical expression. Taking 5, multiplying it by some number, which we don't know, let's call it b, 2 times in a row. So if we multiply by b 2 times in a row, that's kind of like b squared. In fact, it is b squared, and we end up with 245. So I just took all the things that I thought about and then expressed in words and put into a mathematical sentence, which you probably know how to solve for the unknown being b, the base, the multiplier. Well, if we take 5 times b squared, we'd have to do b squared first and then multiply by 5, which means that this 245 is 5 times bigger than b squared. That's a long way of saying just divide both sides by 5. So we just get b squared 245 divided by 5 is 49. And what squared is 49? Look at that, it's 7. Now that's kind of the mathy way, the equation way to do that. You could have worked that out other ways, trial and error, or some other method. But we did end up getting our b value, which means that the repeated multiplier is 7 to the x, and we're starting with 5 in this case. So 5 times 7 to the x. Okay, so filling in the table, if we just multiply by 7 one time for starting with 5, we get 35. And once again, I put this into the graphing calculator, so I can just read right off my table of values. 245 times 7 is 1715, and 1715 times 247 is 12,005. 12,005. Okay, so getting the equation, finding that multiplier, that's your b value. If you have the output when x is 0, you have your a value. You might have to do other things to get that sometimes, but in both of these cases we had the a value right in the table. And that is how you go from an equation, from a table to an equation. All right, let's go on to the next one. All right, this time we have the equation, so it shouldn't be too hard to build the table here. X and y, let's do it like the tables were above, 0, 1, 2, 3, and 4. 1/2 to the 0 power. I'll go ahead and write that one out. I'm not going to write all these out, but this one I will. This comes first, and like we said, any number to the 0 power is 1. So 1200 times 1 is, of course, 1200. That makes sense. That's our starting point, so to speak, our y-intercept. Then I can go ahead and do a little sketch of the graph here. And let's call this 0, so this is 1200. There's our first point on the graph. Okay, plugging in a 1, I'm just going to do this one mentally. 1/2 to the first is 1/2, and 1/2 times 1200 is 600. And you can almost see the halving happening now. 1/2 to the second is 1/4, so we're taking a fourth of 1200. A fourth of 1200 is half of 600. 1/2 to the third is 1/8. Now we're 1/8 of 1200, and 1/8 of 1200 is 1/2 of a fourth. Basically, we're halving if we increase x by 1 each time. And if we transfer this to a graph, on the y-axis, if you just see if I cut that 1200 in half, and then I cut that 600 in half, and then the 300 in half, oops, only 150, not 1500, and the 150 in half, you can see this halving happening on just the y-axis, so you can kind of see it in a linear fashion. Now if we add that second dimension, the x-axis, then we get this nice curve that gets closer and closer and closer. And if we kept going, it would just get closer, closer, and closer, but never touch the x-axis. And of course, this is a continuous function. So we might connect those dots. Okay, that's number 2. Let's move on to the last one here, application in the real world, where we have concert ticket prices increasing from 150 to 162. They do say they increase exponentially, so that's an important piece of information. That means that there's some multiplier that goes from 150 to 162. We got to find that multiplier. And then that multiplier is going to repeatedly multiply by the higher ticket price. So how do we find that multiplier? That's just a matter of division. Oops, not by x, by 150 to solve for x. and 1.08. So 1.08 is your multiplier, and that means that 108% is your growth rate, daily percent of increase. So what will the cost of a pair of tickets be a week from now? Why don't we write an equation that'll help us do that? Oh, this time I'm not going to use y. I'm going to be cool. I'm going to go cost as a function of the number of days. C of D is equal to, it says 162 is today, so I'm going to start with 162 today. I'm going to multiply that by 1.08, that would be tomorrow. And I'm going to raise that to the power of D days. So if I put a 0 in for days, that would be right now today. And 1.08 to the 0 is 1, and 1 times 162 is 162. So that would be the cost today. Could even make a little table for that. Days and cost is a function of days, 0, 162. Okay, I could just keep going until I got to a week from now with my table, but that would be time consuming and I have to continue multiplying by 1.08. I could put it into a graphing calculator and just go to the table and get 7 pretty quickly. That would be a faster way to do it. Or I could just evaluate C of 7. C of 7 is the cost after 7 days, 1 week. And that would just be 7 increases of 8% starting at 162. And if I did that, I think I am getting, what do we get? $278. So any of those ways should get you to $278. Okay, so don't wait. Get your concert tickets today. And then 2 weeks ago, well, multiple ways to do this as well. You could go backwards now in the table, go to -1, and that would be dividing by 108% or dividing by 1.08. We already know what the first one is, 150. That was yesterday. It told us that. That's how we got to 1.08 in the first place. You could keep going back all the way to -14. But again, now we have 14 places to go, and that's even longer. We could go to our table in the graphing calculator and keep going back to -14. Or, we've got a function here. Let's just evaluate it for -14. And hopefully this is where it makes sense a little bit, that a negative exponent doesn't necessarily mean a negative result. We're not going to have a negative ticket price. It's just going to keep getting divided by 1.08, so it's going to get smaller and smaller. So when I put this into the calculator, I got $55. Now there are limits to the value of this function. I mean, the ticket prices didn't start at 0. On the very first day they put them for sale, they didn't say they're free, come on, and then increase from there. So there was a minimum, so some parameter, and then they're not going to increase to $1 billion either, so there'll be some maximum before the concert date. But you can see what's happening and how this might play out in the real world. Hope that helps. Take care.